Hello there, folks. It's me, Bhoomika, again. As you already know, we are through with our in depth discussion over some of the questions of the JEE main paper, which was conducted on the 25th of February in the second shift. Today, we are going to resume our discussion over the remaining questions of the same paper. Alright, so without any further delay, let's get started. Next up, we have this question from Matrices. Let's check it out. In here, we are given a matrix of order 2 cross 2, which is capital A, and the entries are involving alpha and beta. Can you see that? Also, there is a beautiful property which is being exercised by A, that its product with its transpose is equal to identity matrix of order 2. Then, you have to compute the value of the expression alpha to the power 4 plus beta to the power 4. Now in here, this question is extremely straightforward. The only thing you have to do is exploit this property to the fullest. Because from here only we can extract out the value of our required expression alpha raised to the power 4 plus beta raised to the power 4. Okay, so A is nothing but 1 minus alpha, alpha, beta. Multiply with its transpose. How do you obtain the transpose of a matrix? Just interchange the rows and the columns. Bingo, you're done. So first row becomes the first column. Second row becomes the second column. This is A and this is A transpose. Their product, their matrix multiplication is equal to the identity matrix of order 2, which is 1, 0, 0, 1. Perform the multiplication on the left hand side. What will you get? First row into first column gives you 1 plus alpha square. Then first row into second column gives you alpha minus alpha beta. Then second row into first column gives you alpha minus alpha beta, and second row into second column gives you alpha square plus beta square. This is 1, 0, 0, 1. So left hand side is a 2 cross 2 matrix. Right hand side is a 2 cross 2 matrix. Two matrices of the same order are equal if and only if each of the corresponding entries of both those matrices are same, identical, photocopy. So, if these two matrices are equal, that means the 1/1th element of both these matrices will be equal, isn't it? This gives you 1 plus alpha square will be 1. This implies alpha square is 1 minus 1, that is 0. Don't forget, we are computing the value of the expression alpha to the power 4 plus beta to the power 4. If alpha square is 0, alpha square whole square is also 0. That means alpha to the power 4 I know is 0. The only thing now that I have to compute is beta to the power 4 equals what? Okay, so you can see the 2/2th entry also of both the matrices will be same. So from here you will get alpha square plus beta square equals 1. But alpha square I know is 0. That means beta square is 1. The moment you know that beta square is 1, that gives you beta square whole square is 1 square, which is again 1, landing you with the value of beta to the power 4 equals 1. So alpha to the power 4 is 0, beta to the power 4 is 1. That means this expression has value 0 plus 1, which is 1, sitting in option A. You're done. All right then, this is the question from functions. Let's quickly check it out. In here, it's talking about two sets A and B such that A has cardinality 3 and B has cardinality 5. From A to B, the total number of 1, 1 functions is given as x. Next, the two sets which are being talked about are A and A cross B. From A to A cross B, the total number of 1, 1 functions is given as y. If these are the descriptions of x and y, using it, we have to compute the relationship between x and y which prevails out of the given 4 options. So in order to deduce that relationship, we should explicitly compute x and compute y. So let's first of all target upon x, which is the total number of 1, 1 functions from A to B, keeping in mind that cardinality of A is 3 and cardinality of B is 5. Realize that the only concept this question is demanding from you is the definition of 1, 1 or injective function from A to B. A correspondence from A to B is said to be 1, 1 when each member of set A has a unique and distinct image in set B. We know this. So A has 3 members, let's call them x1, x2, x3. B has 5 members, let's call them y1, y2, y3, y4 and y5. Yes? Now, A function f from a to b will be 1, 1, or let's say it is 1, 1. F is a 1, 1 function from a to b. Then what are the rules that it will satisfy under the correspondence of members of a to b? Number 1, x1 should be mapped to one element of set B. There are 5 choices with me to map x1 to. Do you agree? So there are 5 ways in which I can map x1 to one member of set B. Now, once x1 has been mapped to any one of the 5 members of set B, then there are only 4 ways remaining to map x2 to. So I have 4 ways, 4 choices, 4 possibilities to map x2. Why not 5? Why 4? Why did one possibility reduce for x2? Because under the 1-1 mapping, the images have to be distinct. So if x1 had 5 choices, once x1 has been mapped to any one member, now x2 has only remaining 4 choices. Now if x2 also is mapped to any one of these 4, x3 will have how many choices? 3 choices. So there are 3 ways to map x3. So individually, if there are 5 ways to do the first job, 4 ways to do the second job, 3 ways to do the third job, then total number of ways of doing all the 3 jobs, the first and the second and the third, is 5 into 4 into 3. That means total number of ways in which x1, x2, x3 can be mapped to the members of set B such that the correspondence is 1, 1 are 5 into 4 into 3, which is 60. This is the total number of 1, 1 mapping from A to B, which is my x. So I have deduced x. X is 60. Using the same logic, we are going to compute y now, which is the total number of 1, 1 functions from set A to set A cross B. Now A has what cardinality? 3. So let's take the members as x1, x2, x3. That's what we did, right? What about the cardinality of A cross B? The number of members in A cross B is number of members in A into number of members in B. Do you agree? Because A and B both are non-empty sets. Agreed? So A has 3 members, B has 5 members. That means A cross B will have 15 members. Let's call them Y1, Y2 and so on. Or let's say Z1, Z2 and so on till Z15. I want a mapping to be 1, 1 from A to A cross B. So let's begin with x1. Okay, we'll begin with x1. There are 15 ways in which you can map x1 to a member of set A cross B. So there are 15 ways to map x1. Now, once x1 has been mapped, x2 has remaining 14 ways to get mapped. So now I have only 14 choices left to map x2 to. So 14 ways to map x2. And now when x2 also has been mapped to one of the members of set A cross B, now there are again one less. 13 ways to map x3. Do you agree? Because again, the images have to be distinct, right? So, if there are 15 ways to do the first job, 14 ways to do the second job, 13 ways to do the third job, then the total number of ways to do all the 3 jobs simultaneously or one after the other are 15 into 14 into 13. Yes? I'm just using my fundamental theorem of counting, nothing else. Basics of PNC, that is permutation and combination. Alright, so total number of 1, 1 mappings from set A to A cross B are 15 into 14 into 13. This is my y. Okay, now I am going to extract out this expression and actually post-mortem it. See how? Y is 15 into 14 into 13. Somehow I have to bring into x in picture so that I have an equation involving both y and x. And I know x is 60. I know 15 into 4 will give me 60. So let me artificially multiply by 4 and to balance it out, divide by 4 as well. I just multiplied by 4 and divided by 4 so that 15 into 4 becomes 60 and 60 is nothing but x. So I have this left with me. I have an equation involving both x and y. I'm just going to resolve this. What will this give me? This gives me 2y equals 91x. And 2y equals 91x is the very relationship between x and y which is sitting in option B. So this question only demanded from you the concept of, first of all, definition of 1, 1 function, And next is the fundamental theorem of multiplication, which is the fundamental theorem of counting, to compute the total number of 1, 1 functions from the first set to the second set. That's it. Let's check out this wonderful question. It is saying that there is this curve, which is of second degree, you can see, intersecting the line x plus y equals 1 at 2 points P and Q. Then the angle subtended by the line segment PQ at origin is what? So let's first of all visualize what's going on in the Cartesian plane. You can clearly see that this is nothing but an ellipse, isn't it? In order to convert it in the standard form, I'll divide both sides by 2. So I'll have x squared by 2 plus y squared by 1 equals 1. You can see the denominator of x squared is greater than denominator of y squared. So this is obviously going to be the standard horizontal ellipse with major axis along the x-axis. All right. So these are my points, root 2 and minus root 2, and this is 1. Cool. There is a line x plus y equals 1 which is intersecting this ellipse at 2 distinct points. Now realize one thing, when I plug in x as 0, I get y as 1. So one of the points is 0, 1 which is lying on the line. And when you plug in y as 0, you get x as 1. That means 1, 0 is another point lying on this line. So when you join both these points, you get this to be the line x plus y equals 1. This line is intersecting my ellipse at 2 points P and Q. So one point of intersection is P, other point of intersection is this Q. This PQ segment is subtending an angle at origin. Can you look at that angle? This is that angle. And it's very simple to make out that this angle is actually obtuse. Are you understanding? Now, this is my origin. If you extend this backward, what are you getting? Two lines, line 1 and line 2, which are intersecting each other at origin. And I want to compute the obtuse angle between them. Isn't it? That's the scene. The acute angle between them, let's call it theta. If somehow I get theta, then obtuse angle between them will be pi minus theta. That's it, end of the story. Till there I have to reach. But in here, in this setup, you can clearly recall the usage of homogenization. Isn't it? You have a 2-degree curve and you have a line which is intersecting that curve at 2 distinct points. Yes, using the method of homogenization, you can actually get the combined equation of the two lines L1 and L2. And that is the agenda. So let's use the concept of homogenization. Look at this curve. Each term is having a degree 2 except the right hand side constant, which is 2. So I am going to convert it to second degree by multiplying it with 1 square. 1 from here is x plus y. So I will be writing 1 as x plus y. So 1 square will be x plus y square, right? Now you open this up, right hand side becomes 2x square plus 2y square plus 4xy. When you simplify, what you end up getting is x square plus 4xy equals 0. Okay, and this equation is comparable with ax square plus 2hxy plus by square equals 0, which represents the combined equation of the pair of straight lines intersecting each other at a single point, which is origin. On comparing, you get the value of a to be the coefficient of x square, that is 1. You get the value of h to be half of coefficient of xy, that is half of 4, that is 2. And the value of b is coefficient of y square, which is 0. Yes, now I know whenever I have a pair of straight lines intersecting at origin, then the acute angle between them is given by this formula. So this formula is going to give us the acute angle theta that we have to find, okay? So plug in the values here. What do you get? What do you get? Well, in place of h you plug in 2, in place of a you plug in 1, in place of b you plug in 0. This will give you what? 4. Okay, so tan theta is coming out to be 4. Fine, so theta I can say is tan inverse 4. This is the acute angle between the two lines L1 and L2. I want the obtuse angle between them. So the obtuse angle between them will be what? obtuse angle between them will be pi minus theta, that is pi minus tan inverse 4. Yes? Okay. What does this give you? Tan inverse 4 I can write as cot inverse 1 by 4. Am I right? Tan inverse 4, or I should say tan inverse x, is cot inverse 1 by x when x is positive. 4 is positive, so tan inverse 4 can be written as cot inverse 1 by 4. But I know as a matter of fact that tan inverse 1 by 4 plus cot inverse 1 by 4 is pi by 2. So cot inverse 1 by 4 can be written as pi by 2 minus tan inverse 1 by 4. This gives you what? Pi by 2 plus tan inverse 1 by 4 to be the very obtuse angle that I was searching for, which is sitting in option A. So the only point you had to realize was that there was an ellipse and there was a line which was intersecting the ellipse at two distinct points. When I formed the angle subtended by that PQ line segment, it came out to be obtuse. I wanted to find it. So I realized that when I actually back extended the two lines, I got pair of lines which are intersecting at origin. Yes, so somehow if I can get their combined equation, from there on I know how to compute the angle between them. So I used the homogenization process to get the combined equation of those pair of two lines. From there I used my tan theta formula to get the acute angle between them, and pi minus the acute angle gave me the obtuse angle between them, which is the very angle sitting in option A. Got the strategy? Great. Now, coming from the world of indefinite integrals is this beautiful question. It is giving you a very fancy large integral and asking you its final value out of the given four options under the condition that x is strictly positive. Okay, now no need to get scared by looking at this integral. What you have to just focus on is this integrand involved here. And the terms which are together building up this integrand have a very similar look. Each one of them looks like e to the power log of something. So in order to dissolve this integrand into something simple to deal with, you have to just keep two things in mind. Number one, e to the power log of whatever to the base e is that whatever. And number two, a log input to the base e is log of that input to the power a, base remains the same, e. Basically, this multiple a moves to the power of the input. Okay, these are the only two concepts which will be useful here to simplify my integrand and hence compute the final integral. Do you get it? So look over here. First of all, 3 log 2x will become log of 2x cube. Yes, so this will give you e to the power log of 2x cube. But e to the power log of input to the base e is that input only. So this is nothing but 2x cube. Okay. Similarly, come over here in the next term. 5 remains as it is. This 2 moves to the power. So you are left with e to the power log of 2x whole square. But again, this will just be 2x whole square. Okay. Similarly, come over here. This will just be x to the power 4. Come over here. 5 as it is. This will be x to the power 3. Come over here. Minus 7 as it is. This will be x to the power 2. Hence, my integrand now looks like 2x cube plus 5 into 2x square upon x to the power 4 plus 5x cube minus 7x squared. So this is now the integral that I have to solve. Did you realize how beautifully I got rid of the exponential and the logarithmic terms involved here, which were initially scaring me and intimidating me? Yes? So now we have a smooth sail to go on. Cool then. Okay. So 8x cube, that is what it becomes because 2x whole cube is nothing but 8x cube. Next you had 5 into 2x whole square, that gives you 5 into 4x square. In here you had x to the power 4, this is 5x cube, this is minus 7x square. Let's simplify this further. This gives you 8x cube plus 20x square in the numerator and denominator remains as it is. One thing I want you to notice. In the denominator, from each term I can extract out x square common, and from the numerator again I can extract out x square common. I was given already in the question that x is strictly positive, which implies x square is strictly positive, and using that concept I can cancel out x square from both numerator and denominator. So this will give me integral of x square common 8x plus 20 upon again x square common x square plus 5x minus 7 dx. I can confidently cancel out x square. Why? Because it is strictly positive. When your real number is positive, its square is also positive. Yes, no problem. So now, focus on one thing. See, 8x plus 20 can be written as 4 common 2x plus 5. And notice one thing here. Differentiation of x square is 2x and differentiation of 5x is 5. You have got the hint. You simply have to take the denominator x square plus 5x minus 7 as t, use the method of substitution, and within no time you will be able to reach to the answer. Differentiate, you will get 2x plus 5 dx equals dt. Okay, so what does this give you? Integral 4, and then here you will have just dt upon t. Isn't it? Because 2x plus 5 dx is nothing but dt, and complete denominator is my t. So 4 I can take out common. Integral of 1 by t is ln mod t plus constant of integration. Now in place of t, just plug in this expression. So your final answer of the integral is 4 times ln of mod of x square plus 5x minus 7 plus constant of integration, which is sitting in option C. Easy peasy, isn't it? Fine. Coming from the wide umbrella of coordinate geometry is this question. Let's check it out. So in here we have two curves. One is the ellipse, other is the hyperbola. We are aware of the explicit equation of the ellipse as x square by 25 plus y square by 16 equals 1, which resembles the standard equation of the ellipse x square by a square plus y square by b square equals 1, wherein you can clearly make out a is greater than b. That means the ellipse given over here is the standard horizontal ellipse with major axis along the x-axis and minor axis along the y-axis. So this information I have about the ellipse. Cool? Now, read through the question very carefully because each word, each statement is going to be used in the solution. The hyperbola given over here is passing through the foci of this ellipse. The foci of the standard horizontal ellipse I know is given by plus minus AE, 0, where E is the eccentricity of this ellipse. Let's denote it as E1. My hyperbola is passing through the foci of this ellipse. That's number one. Number two, the transverse and conjugate axis of the hyperbola are coinciding with the major and minor axis of the ellipse. This simply implies that the hyperbola is the standard hyperbola. Yes, in fact, the standard horizontal hyperbola, which is going to definitely look like x square by a square minus y square by b square equals 1. This is how it will look like. Alright, also you are given that the product of eccentricities of both the ellipse and the hyperbola is equal to 1. So let's say E2 is the eccentricity of the hyperbola, then E1 into E2 is given as 1. Using each of these pieces of information, you have to compute the explicit equation of your hyperbola. In order to do that, we have to obviously catch hold of capital A square and capital B square values. How are we going to do that? See, one by one, step by step, take the baby steps and you will reach to the answer very, very nicely. See, you have your ellipse with yourself. Yes, I know A square is 25, I know B square is 16, A is greater than B. My ellipse is standard horizontal ellipse, its eccentricity is E1. What is the relationship between A, B and E1 which will be satisfied here? You know B square is equals to A square into 1 minus E1 square. This is for ellipse. Plug in the values. Plug in the values, you get 16 equals 25 into 1 minus E1 square. This will give you 16 by 25 equals 1 minus E1 square, or E1 square is 1 minus 16 by 25, which gives you 9 by 25, thereby implying E1 is 3 by 5. So A I know is 5 B I know, or I should say E1 I know is 3 by 5. Now the coordinates of foci of the ellipse will be plus minus AE1 comma 0, which is nothing but plus minus 3 comma 0. Do you agree? A is 5, E1 is 3 by 5. So A into E1, 5 cancels out, you're just left with 3. So these are the coordinates of the foci of the ellipse. Now my hyperbola, which I had taken as x square by a square minus y square by b square equals 1, this hyperbola is passing through these coordinates. It's passing through the foci. That means the coordinates of foci will satisfy the equation of my hyperbola. So in place of x you plug in 3, in place of y you plug in 0. What you will get is 9 by a square minus 0 equals 1, which implies 9 equals a square. What are we chasing? We are chasing a square and b square. A square is known to us. What about b square? In order to fetch that, we are going to exploit the property that E1 into E2 is 1. What about E2? Do we have E2? Let's find out. See, E1 is 3 by 5. E2 I don't know. The product is 1, which means E2 is 5 by 3. Yes, I need b square. I know the relationship between a square, b square and E2 corresponding to the hyperbola. What is it? Well, b square is equals to a square into E2 whole square minus 1. Yes, remember? So b square remains as it is. A square we just computed is 9. And this is 5 by 3 whole square minus 1. What is this? 9 into 25 by 9 minus 1. This gives you 9 into 16 by 9. 9 cancels out, you're just left with 16. So b square is coming out to be 16. So what does your hyperbola look like? X square by 9 minus y square by 16 equals 1. Option B, absolutely correct. Coming up next from the family of limits is this question which belongs to a very famous and popular category, that is computing a definite integral as limit of a sum. You can clearly make out the expression that you can see here has limit and this jumbo expression which is sum of many terms. If I somehow dissolve this large expression into a compact form involving summation, then clearly the look of this expression will be limit of a sum. Yes, then we're going to convert it into definite integral, and from that point onwards, the solution is going to be a cakewalk. So, my agenda right now is to dissolve this enlarged expression, this humongous expression, into a compact summation form. How am I going to do that? Carefully observe the terms sitting in this expression, in this sum. You have n upon n plus 1 whole square. Then you have n upon n plus 2 whole square. Next will be n upon n plus 3 whole square. So you can see the succession. The numerator is always n and denominator is n plus something whole square. So this last term I can write 2n minus 1 whole square as n plus n minus 1 whole square. Isn't it? So from second term onwards, I have written each term as n upon n plus something whole square. What about the first term? I am going to write it as n upon n plus 0 whole square. Wow! I played so smart. I actually converted each of the terms sitting in this jumbo sum expression into the similar look. Isn't it? N upon n plus something whole square, where that something is varying from 0, 1, 2, 3 till n minus 1. So now I can definitely in the next step write this as summation of n upon n plus r whole square, where r is running from 0 to n minus 1. My expression was limit n tends to infinity of this humongous expression, which now is becoming very petite and small. This looks like limit n tends to infinity of this summation expression. So this is limit of a sum. I know I can transform it to definite integral, but the rules that I have to keep in mind are that I need r by n to be created somehow. I have r here. I need r by n to be created because do you remember we take r by n to be x. So that's how my integral is in terms of x or with respect to x, right? In order to create r by n, what I'm going to do is, I won't disturb this limit. I won't disturb this summation. I won't disturb the numerator n. What I'm going to do is I'm going to take out n common from here. So this will give me 1 plus r by n and all of this whole square. Did you see how easily I created r by n here? Now, this in the next step gives me limit n tends to infinity, summation r running from 0 to n minus 1, n upon n square into 1 plus r by n whole square. So this n cancels out. What you are left with? Carefully write it, okay? Limit n tends to infinity, summation r going from 0 to n minus 1, 1 upon 1 plus r by n whole square into 1 by n. We are just one step away from writing this exact same thing in the definite integral format. See, you know the rules? Yes, the steps you are aware of. Limit and summation together will convert to integral sign. In here, r by n will be treated as x. So my integrand will be 1 upon 1 plus x whole square. Yes, and n tends to infinity. 1 by n tends to 0. It's getting smaller and smaller. That I'm going to treat as dx. And what about the limits of the integral sign? Well, that is going to come from these limits over r, which are about the summation. So r is varying from 0 to n minus 1. I need limits over x. X is what? R by n. So I'm going to divide throughout by n. This gives me r by n is varying from 0 to 1 minus 1 by n. Now, n is approaching to infinity, so 1 by n will approach to 0. This gives me r by n, that is x, will vary from 0 to 1. Great. This is the integral that you have to solve now, which is a cakewalk, isn't it? So the integral comes out to be what? 1 plus x to the power minus 2 plus 1 upon minus 2 plus 1, where the limits are varying from 0 to 1. So this gives you 1 plus x to the power minus 1 minus here 0 to 1. So this gives you minus 1 upon 1 plus x from 0 to 1. And what is this? Minus 1 by 2 minus 1. Minus 1. So this is plus 1. Yes? And 1 minus 1 by 2 gives you 1 by 2. Bingo. 1 by 2 is your final answer sitting in option C. Done.